Right now, in the room around you, something is happening that almost no one ever stops to notice. Light is leaving a lamp, or the soft glow of a screen, or the last gray light of the evening sky, and it is traveling in every direction at once, bouncing, scattering, slipping through the air, and reaching your eyes so gently that you call the whole process simply seeing. But somewhere along the way, that light is passing through something solid, something with weight and structure, and a history stretching back thousands of years. And it is doing something that, if you think about it slowly enough, is almost impossible to believe. It is moving through solid matter, as if the matter were barely there at all. Maybe it is the window near your bed, holding back the night air, while somehow letting every photon of streetlight drift through undisturbed. Maybe it is the glass of water on your nightstand, catching a dim reflection on its curved surface, while the light inside still reaches your eye from the far side, bent but unblocked. Maybe it is the screen in your hand, thin and cool, with light pouring upward through layer after layer of engineered material before it ever reaches your eyes. In every one of these cases, you are witnessing a kind of quiet miracle that became so common, so unremarkable, that humans stopped marveling at it centuries ago. We call the material glass, and we call what it does transparency. And tonight, slowly, gently, with no rush at all, we are going to take that everyday miracle apart and understand what is actually happening inside it. It helps, before we go any further, to let go of the idea that transparency is simply the absence of something, that a clear material is just an empty material, a kind of nothing wearing the shape of a something. This is one of the most natural assumptions a mind can make, because our intuition about solid objects comes from touch and from the everyday experience of things blocking other things. A wall blocks a ball, a curtain blocks light. So surely, the thinking goes, a transparent object must simply be a wall that forgot how to block, a material with gaps built into it, tiny tunnels through which light slips unopposed, like a fence with enough space between the boards for a cat to pass through untouched. But that is not what is happening in the glass beside you. Glass is not full of holes, it is not thin, it is not a lattice of empty channels waiting for light to find the right gap. If you could shrink yourself down and walk through a pane of window glass, atom by atom, you would find no clear corridor, no straight, obliging pathway leading from one side to the other. What you would find instead is an almost unbroken crowd of atoms, packed close together, humming with their own quiet vibrations, arranged in the strange and beautiful disorder that we will spend a good deal of time exploring later in this narration. And yet, despite this crowd, despite this density, light passes through it, as though the crowd simply is not there for it. That is the puzzle we are settling in with tonight. Not an absence of material, but an unusually cooperative relationship between material and light. Transparency, properly understood, is not a gap in matter, it is an event. It is something that happens over and over, trillions of times a second, as light and atoms meet each other, and, for reasons we are about to unfold slowly, decide not to interact in the way you might expect. To understand why this feels strange, it helps to remember what light actually is doing when it meets most other materials. Consider a piece of ordinary paper, warmed by afternoon sun,
or the wooden surface of a nightstand, patient and still, beside your bed. Light strikes these things constantly, and yet you cannot see through either of them. The light does not vanish, of course. Nothing so dramatic occurs. Instead, the atoms and molecules that make up the paper, or the wood, absorb some of that light, and then release it again in different directions, and often at different energies, so that the neat, organized beam of light you started with becomes a scattered, tangled mess, bouncing every which way, some of it turned into gentle warmth. You perceive that scattered light as color, as the surface of the object, as the visible boundary between one solid thing and everything around it. Opacity is not really about blocking light. It is about disorganizing it so thoroughly that no coherent image can pass through to the other side. Glass and other transparent materials do something altogether different, and it is worth letting that difference sit in your mind for a moment before we begin to explain it. When light enters a pane of glass, it does not stop, and it does not scatter into 100 confused directions, and it does not get absorbed and re-emitted as a formless glow. Instead, remarkably, it continues onward, largely maintaining its direction and its order, right through the crowded interior of the material, and emerges on the far side, still carrying an image, still carrying color, still carrying the shape of whatever it started as. A photon that begins its journey as part of the outline of your hand can pass through a window pane and land on the retina of someone standing outside, and they will see your hand, not a smear, not a blur, but your hand, recognizable in nearly every detail. This is not a small thing. This is light surviving a journey through solid matter, with its information almost entirely intact. For most of human history, this was simply accepted as the nature of certain rare and valuable materials. Ancient civilizations along the eastern Mediterranean discovered, likely by accident, that heating sand, together with certain minerals, produced a hard, cool substance that could be shaped while soft, and would then hold its form, sometimes clear enough to glimpse shapes through it, though early versions were often clouded, greenish, or full of tiny bubbles trapped from the moment of their making. It would take many centuries of careful craftsmanship, patient experimentation by unnamed artisans working in small workshops, and gradual refinements in furnace temperature and ingredient purity, before humans could produce glass clear enough to rival what we now consider ordinary window glass. And even as that craft matured, no one making it, however skilled, understood why it worked. They knew which sands produced clearer results. They knew which minerals reduced the greenish tint. They knew how long to cool a piece before it would crack under its own trapped stresses. But the actual reason light could pass through their careful creations, while stone or wood could not, remained, for thousands of years, a beautiful and useful mystery. It is worth sitting with that mystery tonight, the way those early glassmakers might have, without the modern vocabulary of atoms and electrons and electromagnetic waves, simply watching light behave in a way that seems to defy the solid, tangible nature of the material carrying it. Imagine a glassblower in a quiet workshop, centuries ago, holding a glowing gather of molten glass at the end of a long metal pipe, watching daylight glow faintly through even the thick, hot material, long before it had cooled into its final clear form. That person had no theory of light as a wave or a particle. They had no understanding of electron energy levels or the internal architecture of atoms, and yet they were witnessing, firsthand, night after night, day after day, the very phenomenon we are going to spend the rest of this narration slowly, gently unpacking. They simply called it clarity. We now know it involves a very specific, very delicate relationship between the energy carried by light and the energy allowed inside the atoms that make up the glass itself. A relationship where the light, in a sense, does not find anything to grab onto. But that explanation, the real explanation, requires understanding light itself a little differently than we usually do, not as a simple ray traveling in a straight line, but as a wave, oscillating, carrying a very specific kind of energy that depends on its color, its frequency, the rhythm of its invisible pulse.
So let us begin there, gently, in the next part of this journey. Let us look more closely at what light actually is, stripped of the assumptions we usually make about it, before we bring it back to meet the atoms waiting quietly inside the glass around you. Let's start with something you already know without knowing you know it, which is that light has color, and color is not just a matter of taste or perception, it is a matter of measurement. Somewhere between the moment sunlight leaves the sun and the moment it lands warm on your skin, it has been traveling as a wave. Not a wave like water rolling toward a shore, though the image is a useful starting point, but a wave of something stranger, something that does not need water or air or any material at all to move through. It is a wave made of electricity and magnetism, endlessly trading places with each other, each one giving rise to the other, over and over, as the whole pattern moves forward through space at a speed so fast that it can circle the Earth roughly 7.5 times in a single second. This is worth resting on for a moment, because it is genuinely strange if you let yourself feel the strangeness of it instead of rushing past it the way we usually do. A changing electric field creates a changing magnetic field nearby. That changing magnetic field then creates a changing electric field a little further along, and that electric field creates another magnetic field, and so on, each one handing the energy off to the next like a relay of invisible runners, and this handoff is what we call an electromagnetic wave. Visible light is simply one small, particular range of these waves, the range that happens to be the right size and rhythm to be caught and interpreted by the particular light-sensitive cells at the back of your eyes. The physicist who first wrote down the mathematics describing this handoff was a Scottish scientist named James Clerk Maxwell, working in the 1860s, and it is worth pausing to imagine him at his desk, filling pages with equations about electricity and magnetism, and then noticing, almost as a surprise even to himself, that his equations predicted the existence of waves that would travel through empty space at a speed that matched, almost exactly, the already measured speed of light. He had not set out to explain what light was. He had been trying to unify two things that seemed separate, electricity and magnetism, and light fell out of the mathematics as a kind of unexpected gift. It is one of the quieter, more elegant moments in the history of science, a person discovering that two mysteries were secretly the same mystery all along. Now, within this broader family of electromagnetic waves, the ones your eyes can detect occupy a narrow band, and what distinguishes one color from another, physically, is the wavelength of the wave, which is simply the distance from one crest of the oscillation to the next. Imagine, if it helps to picture it, gentle ripples spreading across the surface of a still pond after a pebble drops in,
Some ripples might be spaced close together, crest after crest arriving in quick succession. Others might be spread further apart, more leisurely, more stretched out. Light works in an analogous way, though its ripples are not made of water rising and falling, but of electric and magnetic fields oscillating in strength, and the spacing between those ripples is almost unimaginably small, measured not in inches or centimeters, but in nanometers, billionths of a meter. Red light, the light your eyes interpret as red, has a wavelength of around 700 nanometers. Violet light, at the other end of what you can see, has a wavelength closer to 400 nanometers. Everything in between, the oranges and yellows and greens and blues, corresponds to wavelengths that fall in that narrow range, each color a slightly different rhythm of the same underlying pulse, and beyond both ends of this narrow visible band, the electromagnetic spectrum keeps going, in both directions, far past what your eyes were ever built to notice. Just beyond red, with even longer wavelengths, lies infrared light, the kind you cannot see, but can sometimes feel as warmth on your face, near a fire. Beyond that, with wavelengths stretching out further still, lie microwaves, and beyond those, radio waves, some with wavelengths longer than a building. And just beyond violet, with shorter wavelengths, lies ultraviolet light, the kind that can, with enough exposure, redden your skin at the beach, and beyond that, X-rays, and beyond those, gamma rays, with wavelengths so short they can slip between the atoms of your own body.
So color, at its heart, is simply a name we give to a rhythm, a particular spacing between the crests of an electromagnetic wave. Your eye did not evolve to measure nanometers directly, of course. It evolved to sort incoming light into a small number of categories using 3 types of specialized cells, and your brain then blends the signals from those cells into the rich experience of color you take for granted every waking moment. But underneath that experience, underneath the redness of red or the blueness of blue, there is nothing more mysterious happening than a wave completing its oscillation more quickly or more slowly. Now here is where the story gains another layer, one that would have seemed almost absurd to Maxwell himself, comfortable as he was with the idea of light as a smooth, continuous wave. In the early years of the 20th century, a small group of physicists, working somewhat independently but building on each other's puzzling results, began to notice that light did not always behave the way a pure wave should. In certain situations, light seemed to arrive not as a continuous, gentle wash of energy, but in discrete little packets, almost like tiny bullets, each one carrying a very specific, non-negotiable amount of energy. A German physicist named Max Planck stumbled onto this idea in 1900 while trying to solve a much narrower, more technical problem involving the glow given off by hot objects, a problem that had stubbornly resisted every attempt to explain it using the old, continuous wave picture of light. Planck found that the puzzle only made sense mathematically if he assumed that light energy came in these fixed little bundles rather than in any amount whatsoever. He treated this at first as a kind of mathematical trick, a convenient fiction to make the numbers work, and it is said he was uneasy with the deeper implications for years afterward. It was Albert Einstein, 5 years later, in 1905, the same remarkable year in which he also published his special theory of relativity, who took Planck's mathematical trick and insisted that it was not a trick at all, but a real description of how light
actually behaves. Einstein was trying to explain a different puzzle, one involving light striking metal and knocking loose tiny particles called electrons, a phenomenon that only made sense if the light itself was arriving in these same discrete packets, later given the name photons. Einstein's explanation of this effect, quietly published alongside the much more famous relativity papers that same year, would eventually earn him the Nobel Prize, not for relativity at all, but for this insight into the particle-like nature of light.
So we are left, and physicists have simply had to become comfortable being left, with two pictures of light that both seem true at once. Light behaves as a wave, oscillating smoothly, its color determined by its wavelength, the spacing between its crests. And light also behaves as a stream of individual photons, each one a discrete little packet of energy, arriving one at a time, countable in principle, like grains of sand rather than a smooth flow of water. These two pictures are not really in conflict, strange as that sounds. They're more like two different lenses for looking at the same underlying reality, and which lens is more useful depends entirely on what question you are trying to answer. And here is the detail that matters most for where our story is headed, back toward that glassblower and the mystery of clarity. The energy carried by each individual photon is directly tied to its wavelength, to its color. A photon of violet light, with its short, tightly spaced wavelength, carries more energy than a photon of red light, with its longer, more relaxed wavelength. This might seem backward at first, since we tend to think of energy in terms of size or intensity, but the relationship is precise and unwavering. Shorter wavelength, tighter rhythm, more energy packed into each individual packet. Longer wavelength, more leisurely rhythm, less energy per packet. This is not a matter of brightness, of how many photons are arriving each second, but of how much energy each single photon carries on its own, a fixed quantity determined entirely by its color. And it is this specific, fixed amount of energy carried by each photon of visible light that will turn out to matter enormously once we bring these photons into contact with the atoms waiting quietly inside a piece of glass. Because atoms, it turns out, are remarkably picky about which amounts of energy they are willing to accept. Let's slow down and look at what glass actually is, down at the level of atoms, because the pickiness we just mentioned depends entirely on what those atoms are and how they're arranged. And the arrangement, it turns out, is stranger than most people ever stop to consider. Ordinary glass, the kind in your window right now, or in the lamp beside your bed, is mostly made of one simple, humble ingredient: silicon dioxide, sand, essentially, the same stuff that makes up beaches, that gets tracked into cars after a day at the shore, that squeaks underfoot when you walk barefoot across a dry riverbed. Silicon dioxide is built from two elements, silicon and oxygen, and in nature, it usually shows up in a form called quartz, which is crystalline, which means its atoms are arranged in a strict, repeating, orderly pattern, over and over, like tiles laid across an enormous floor by someone with a great deal of patience and an unwavering ruler. Each silicon atom in this structure likes to bond with 4 oxygen atoms, and those oxygen atoms, in turn, bridge over to other silicon atoms, forming a kind of 3-dimensional lattice, a scaffolding that extends outward in every direction. If you could shrink yourself down small enough to walk through a crystal of quartz, you would find the same pattern repeating with a kind of eerie regularity, the same angles, the same distances, again and again, as far as you could wander. It would feel, in a way, like walking through a city built entirely from identical city blocks, each intersection matching the last. No surprises, no variation, just the pattern continuing on and on into the distance. Now here is where things get interesting, and where the glassblower's furnace comes back into the story. When you take that sand, that crystalline silicon dioxide, and you heat it to an extraordinary temperature, somewhere around 3,000 degrees Fahrenheit, something remarkable happens to that orderly lattice. It falls apart, not in the sense of breaking into pieces you could sweep up, but in the sense that the bonds between atoms begin to loosen, to flex, to let go of their rigid, repeating arrangement. The atoms are still there, still connected to their neighbors by the same kinds of bonds, silicon still reaching out to bond with oxygen, oxygen still bridging between silicon atoms. But the long-range order, that city-wide pattern of identical blocks, dissolves into something much more chaotic. The molten material becomes a kind of atomic soup, atoms and their connections still present, but tumbling and shifting and rearranging freely, no longer marching in ranks. And then comes the crucial part, the part that actually makes glass what it is. As this molten silicon dioxide cools, something unusual happens. In most materials, cooling gives the atoms time to find their way back into an orderly crystalline arrangement, the way water, cooling slowly enough, will arrange itself into the neat hexagonal lattice of ice. But silicon dioxide, when it cools from its molten state, is oddly reluctant to do this. Its atomic building blocks, those little clusters where one silicon links to 4 oxygens, are somewhat bulky and awkward, and they don't slot together easily into a repeating pattern the way simpler, smaller atoms might. So as the temperature drops, the material thickens. The atoms move more and more sluggishly, and before they can organize themselves into a proper crystal, they simply get stuck, frozen in place, mid-shuffle, in whatever disordered configuration they happen to be in, when the cooling outpaced their ability to rearrange. This is the defining feature of glass, and it's worth sitting with, because it's genuinely a little strange when you first hear it described this way. Glass is what chemists and physicists call an amorphous solid. Amorphous simply means without shape, or more precisely here, without a repeating, ordered structure. So glass is solid, undeniably solid, rigid, able to hold its shape, able to be dropped and shatter rather than flow or drip. And yet, at the atomic level, its internal structure resembles a liquid far more than it resembles a crystal. The atoms in glass are frozen in a disordered arrangement, each one still bonded to its neighbors in roughly the same local pattern you'd find in quartz. Silicon, still surrounded by 4 oxygens, but with no long-range order extending across the material. It is, you might say, a snapshot of a liquid, caught mid-motion and locked permanently in place. Picture, if it helps, the difference between a marching band and a crowd leaving a stadium. The marching band, that's your crystal. Everyone in precise rows, precise spacing, the whole formation predictable from any single member's position, because you know the pattern continues identically in every direction. The crowd leaving the stadium, meanwhile, is your glass. People everywhere,
still each one standing a comfortable distance from the people immediately around them, still following the general rules of personal space, and not walking through each other, but with no overall pattern, no rows, no way to predict where the next person will be standing, just by knowing where you are. That local order without global order, that's the atomic portrait of glass. There is another comparison, older and perhaps more poetic, that materials scientists sometimes reach for, and it involves a pile of dry spaghetti versus a pile of cooked spaghetti dropped haphazardly onto a plate. Dry spaghetti, if you've ever bought a box of it, comes packaged with all the strands lying parallel, straight, evenly spaced, ordered, much like a crystal. Cook that same spaghetti, and then let it fall onto a plate, and the strands tangle and curve and cross over one another, in no particular pattern at all, though each individual strand is still the same length, still made of the same material, still connected end to end the way it always was. The ingredients haven't changed. The order has vanished. Now, pure silicon dioxide alone, cooled this way, does indeed make glass, and in fact, this is essentially how the very earliest glass objects were formed. Glass that occurs naturally when lightning strikes sand, fusing it instantly into thin, branching tubes called fulgurites, or the glass that forms in the superheated aftermath of a volcanic eruption, obsidian's more delicate cousins. But pure silicon dioxide glass requires those extraordinarily high temperatures to melt in the first place, and ancient glassmakers, working with the fuels and furnace technology available to them, needed a way to lower that melting point to something more manageable. So they discovered, likely through a great deal of trial and error stretching back thousands of years, that adding certain other ingredients to the sand made the whole process considerably easier. Sodium carbonate, often derived historically from the ash of certain plants, or from natural mineral deposits, works wonderfully for this. Adding it to the silicon dioxide lowers the melting temperature substantially, because the sodium atoms interrupt that atomic network, wedging themselves in among the silicon and oxygen, and breaking up some of the bonds that would otherwise hold the whole structure together at higher temperatures.
But sodium alone creates a glass that is unfortunately soluble in water, which is a problem if you want your glass vessel to survive contact with, say, water. So a third ingredient typically joins the mix: calcium oxide, usually derived from limestone, which restores the water resistance without sacrificing that lower, more workable melting point. This is why the glass in your window, the glass of the lamp beside you, the glass in nearly every drinking vessel and bottle around you, is technically called soda-lime glass. Soda referring to that sodium compound, lime referring to the calcium one. It's a recipe, really, refined gradually over millennia of practical experimentation by people who mostly had no idea what silicon or oxygen atoms even were, who were simply noticing, batch after batch, which mixtures of sand and ash and mineral-produced glass that behaved the way they wanted, that melted at a manageable temperature, that didn't dissolve or cloud or crack. And so what we have, sitting there in a window pane or a drinking glass, is this disordered atomic tangle, this frozen liquid, this crowd without rows, made mostly of silicon and oxygen, with a bit of sodium and calcium woven through, to make the whole thing practical to produce. It holds its shape. It resists being poured or squeezed into a new form, the way an actual liquid would. On any time scale you or I would ever care about, it is every bit as solid and rigid as a crystal of quartz would be. And yet, unlike quartz, it has no long-range order at all, no repeating pattern, nothing a wandering atom-sized traveler could use to predict what lies ahead.
which raises a question worth sitting with quietly for a moment, before we go any further into how light actually makes its way through this strange tangled structure.
Let's turn now to the light itself, and to what actually happens when it meets that tangled structure. Picture a beam of light approaching the window. Before it reaches the glass, before it touches a single atom, it is already doing something strange and wonderful, though calling it a beam of tiny particles marching forward in a line misses most of what matters. Light is also a wave, an oscillation, a rhythmic rippling of electric and magnetic fields moving together through space. And it is the electric part of that rippling that we need to picture clearly now, because that is the part that is about to start a conversation with the atoms in the glass. An electric field, if you have never had cause to think about one before, is simply a kind of influence that pushes on electric charges. It is invisible, intangible, but its effects are not. If you place a charged particle inside an electric field, the field will nudge that particle, will exert a force on it, will try to move it in a particular direction. And in a light wave, that electric field is not steady. It oscillates. It grows stronger, weakens, reverses, strengthens again in the opposite direction, over and over, extremely quickly, many hundreds of trillions of times each second for visible light. So as this wave approaches the glass, it is carrying with it a field that flickers back and forth with tremendous speed, first pushing in one direction, then in the other, then back again, a rhythm so fast that no ordinary object could ever hope to keep pace with it. But atoms, it turns out, are not ordinary objects. And electrons, in particular, are almost absurdly responsive. Every atom in that glass, every silicon atom, every oxygen atom, every sodium and calcium atom, scattered through the disordered network, is built around a nucleus, a dense little core of protons and neutrons, surrounded by a cloud of electrons. Those electrons carry negative charge, and they are, relative to the heavy nucleus they orbit, remarkably light and remarkably easy to nudge. Think of the nucleus as an anchor, heavy and largely immobile on the timescale we're discussing, and think of the electrons as something more like a curtain hung loosely around it, a soft and responsive cloud that can shift and sway without much resistance at all. The electrons are not floating completely free, mind you. They are bound to their atoms, held in place by the electrical attraction between their negative charge and the positive charge of the nucleus, rather the way a curtain is bound to its rod. It can billow and sway in a breeze, but it doesn't simply fly off across the room. So now imagine that breeze arriving. The oscillating electric field of the light wave reaches the electron cloud around some particular oxygen atom deep inside the glass, and it begins to push. Because the field is oscillating, the push isn't steady either. It shoves the electron cloud gently in one direction. Then, as the field reverses, it pulls it back the other way, then pushes again, matching the same staggering frequency as the light wave itself. Hundreds of trillions of oscillations each second. The electron cloud, being light and responsive and elastically bound to its nucleus, the way that curtain is bound to its rod, begins to slosh back and forth in sympathy with the field. It doesn't detach. It doesn't go anywhere permanently. It simply oscillates, tugged this way and that by the passing wave, like a buoy bobbing on the surface of water as a ripple moves beneath it, rising and falling in time with the ripple's rhythm without ever being carried off downstream. This sloshing has a name.
When the negative electron cloud shifts even slightly away from the positive nucleus it surrounds, even for an instant, even by some vanishingly small distance, the atom develops what's called a dipole, a tiny separation of positive and negative charge, positive on one side, negative on the other. And a great many atoms all doing this at once, all across the glass, all oscillating together in response to the same passing wave, is what we mean when we talk about polarization.
Not the polarization of sunglasses, which is a different and more specific idea we might come back to another time, but the more general sense of the word, meaning that the material's charges have been organized, however briefly and however slightly, into these little oscillating pairs, all rippling in step with the light. Here is where something remarkable happens, something that took physicists a long while to work out carefully and mathematically, even though the basic idea, once you have it, feels almost intuitive. An oscillating electric charge does not just sit there oscillating quietly to itself, it radiates. Any charge that accelerates back and forth, the way these electron clouds are now doing under the influence of the light wave, generates its own new electromagnetic wave, its own little ripple of field, spreading outward from that atom in essentially every direction. This is not a separate, mysterious phenomenon. It's the same physics that makes a radio antenna work, charges wiggling back and forth, and broadcasting a wave as a consequence of that wiggling. Every atom in the glass that gets nudged by the incoming light becomes, for the briefest moment, a tiny broadcaster in its own right, a miniature antenna re-emitting a wave at the very same frequency it was driven at. In the rave. Now, this re-emission is not instantaneous. There is a small delay, a tiny lag, between the moment the driving field pushes the electron cloud and the moment the resulting re-radiated wave goes back out. This lag exists because the electron cloud has, in a sense, its own natural tendency, its own preferred way of responding, shaped by how tightly it's bound to its nucleus, and that response doesn't snap into perfect lockstep with the driving field instantly. It takes a sliver of time, absurdly short by any human measure, but not zero. And here is the part that answers the question we left sitting quietly a moment ago. The question of how light manages to travel through something as disordered, as trackless, as a wandering tangle of atoms, with no straight path through it at all. It doesn't travel through by threading some clever route between the atoms, the way a marble might roll through a maze. Instead, what happens is that the original wave and all of these countless tiny re-radiated wavelets, from atom after atom after atom, throughout the glass, add together, combine, interfere with one another, mostly reinforcing each other in the forward direction, the direction the original wave was already headed. The result of all that combining is a single, continuous, forward-moving wave, indistinguishable in its outward behavior from the original, except for one crucial thing. Because of that tiny delay at every single atom it effectively passed through, the whole combined wave ends up shifted slightly behind where it would have been if nothing had gotten in its way at all. This is the deep answer to why light slows down inside glass, or inside water, or inside any transparent material. It is not that photons are literally colliding with atoms one by one, bouncing to a stop and starting up again, pausing for tea at each atomic way station along the route, however tempting and vivid that image might be. Nothing is actually stopping. The light wave, understood properly, never ceases moving forward, even for an instant. What's happening instead is this continuous, collective conversation between the wave and the electrons, a constant nudging and re-radiating
and combining, happening simultaneously across trillions upon trillions of atoms that accumulates, delay by microscopic delay, into an effective slowing of the wave as a whole, a slowing that shows up as light's reduced speed inside the material without any single piece of light actually loitering anywhere. It's a bit like a rumor passing through a crowded room, if you'll permit a rough comparison to hold in your mind as you drift. The rumor doesn't move because one particle, called a rumor, is physically carried from one side of the room to the other. It moves because each person hears it, pauses for just a moment to take it in, and then repeats it onward to the next person, and that small pause, repeated at every single person the rumor passes through, is what makes the rumor's overall journey across the room slower than a single voice shouting straight across empty air would be. No one person held on to the rumor for long, but the accumulation of countless brief pauses adds up to something measurable, something real, even though nothing was ever, at any moment, truly standing still.
And once you have that picture settled gently in your mind, this business of countless tiny antennas, all sloshing and radiating and recombining into one smooth onward wave, there's a natural next question waiting patiently just beyond it, about why this same delicate process, which lets light through so effortlessly in glass, behaves so very differently in a material like metal or in your own hand, blocking the light rather than welcoming it through. Let's set that question about metal and hands gently aside for a moment, resting on the shelf where we left it, and turn instead towards something that has been quietly waiting underneath everything we've said so far. Because so far we've talked about light as a wave, nudging electrons, setting them sloshing back and forth like buoys on a gentle swell. But electrons are not quite as free and easy as buoys on water. They live inside atoms, and inside atoms, and inside the larger structure of a solid material like glass, electrons are picky, fussy even. They don't accept just any amount of energy you try to hand them. And understanding this fussiness, this pickiness, turns out to be the real key to why glass lets visible light through so cleanly, while stopping other kinds of light, kinds you cannot see, almost completely in their tracks. Here is the idea, and there's no need to hold on to every detail tonight, only to let the shape of it settle in. An electron bound to an atom, or bound within the orderly lattice of a solid, can only exist at certain specific energy levels. Rather like a person, can only stand on the actual steps of a staircase and not hover in the empty air between them. You can stand on the third step or the fourth step, but not on some step 3.5. The energy an electron holds is quantized this way, restricted to a kind of ladder of allowed values, with forbidden gaps in between, where, quite simply, there is nowhere for the electron to be. This was one of the strange and beautiful discoveries of the early 20th century, when physicists such as Niels Bohr, working in Copenhagen, began puzzling over why atoms only gave off light at very particular colors, very particular frequencies, rather than any color at all. Bohr proposed, in 1913, that electrons, circling an atom's nucleus, could only occupy certain fixed orbits, certain fixed energies, and that light was emitted or absorbed only when an electron jumped cleanly from one of these allowed levels to another. Not a gradual slide, a jump, a discrete leap, with nothing valid in between. Now, in a single isolated atom, floating alone in empty space,
These allowed energy levels are sharp and few, like a very short staircase with wide gaps between the steps. But glass, of course, is not a collection of lonely, isolated atoms. It is an immense, interconnected network, atoms bonded to atoms bonded to atoms, stretching on, and when you bring that many atoms together, something interesting happens to their energy levels. The neighboring atoms interact, their orbitals overlap and blend, and instead of a few sharp, isolated energy steps, you get whole bands of energy, dense clusters of allowed levels squeezed so close together they behave almost like a continuous smear rather than distinct steps. Picture that same staircase, but now imagine thousands of extra thin little steps have been inserted between the original ones, so many that the staircase begins to look, from a little distance, less like stairs and more like a smooth ramp. That's a band. A crowded neighborhood of allowed energies, born from the collective company of countless atoms bonded together. But here is the crucial part, the part that explains everything we've been circling around. Even though bands are dense and crowded, they are not infinite, and they are not connected to each other without a break. In a material like glass, there exists what's called a band gap, a genuine, forbidden zone of energy sitting between one crowded band, called the valence band, where electrons sit contentedly bound to their atoms, and another crowded band above it, called the conduction band, where electrons would be free to roam through the material, carrying charge, behaving almost like a mist of loose runners, no longer tied to any particular home. Between these two bands lies a stretch of energy that simply does not exist for an electron to occupy, not rare, not difficult, genuinely absent, the way there is no such thing as the temperature between two specific numbers on a scale with actual, physical gaps built into it. A strange thing to imagine, but that is the nature of this particular gap. And for an electron to leap from the valence band up into the conduction band, it needs to absorb an amount of energy that matches the size of that gap almost exactly, not more, not less, precisely enough, or at least closely enough within some narrow tolerance, to make the jump. This is where photons enter the story again, because remember, every photon of light carries a very specific packet of energy, and that energy is tied directly to its color, its frequency. Blue light photons carry more energy than red light photons. Ultraviolet light, sitting just beyond the violet edge of what your eyes can perceive, carries photons with even more energy still. And here is the elegant, almost tidy little fact sitting at the center of tonight's section, the fact that explains so much of what we've been slowly unwinding together. In ordinary silica glass, the kind used in windows, the band gap between the valence band and the conduction band happens to be quite large, roughly 9 electron volts or so, which is a way physicists measure these tiny packets of energy. And the photons of visible light, red through violet, simply do not carry enough energy to make that jump.
They arrive at the glass modestly under-resourced for the task, carrying perhaps 3 electron volts at most on the violet end, and the gap demands something closer to 9. It's rather like showing up to pay an entrance fee with only a third of what's required in your pocket. The door simply will not open for you, however politely you knock. So the electrons in the glass, when nudged by visible light, cannot make that particular leap. There is nowhere for them to jump to. They cannot absorb the photon's energy in that permanent, converting way, turning light into a raised electron and eventually into heat, the way materials that do absorb light tend to. Instead, and here we return gently to the picture from a moment ago, the electrons can only do that smaller, temporary thing, sloshing briefly in response to the passing wave and releasing the energy straight back out again, re-radiating it onward,
contributing to that great continuous relay of nudging and re-emitting that lets the wave pass through the material largely unabsorbed.
The photons pass because there is genuinely no rung of the ladder waiting to receive them. But ultraviolet light tells a very different story, and this is worth sitting with for a moment, because it shows the same glass behaving in an entirely different way depending only on the color, the energy, of the light arriving at its surface. Ultraviolet photons carry enough energy, in many cases, to bridge that band gap successfully. They can be absorbed. The electron makes its leap, all the way from the valence band into the conduction band, and that energy doesn't get released cleanly back out as a matching photon of light. It gets converted, dispersed, often ending up as heat within the material, or triggering other small internal processes. This is part of why ordinary window glass is remarkably good at blocking ultraviolet light, why sitting behind a closed car window on a sunny afternoon can spare your skin from a great deal of the burning rays that would otherwise reach it outdoors, even while the visible sunlight streams through untouched, warming your face without complaint. Infrared light, sitting on the other side of the visible spectrum, tells yet another story again, though for somewhat different underlying reasons we'll unfold with care in a little while. For now, it's enough to notice the pattern taking shape, the way glass isn't simply transparent or opaque as some fixed single property, but rather responds selectively, almost like a very particular gatekeeper, checking not your appearance but the precise energy you're carrying in your pocket, waving through anyone who doesn't have quite enough to cause trouble, and turning away, quite firmly, anyone who arrives with too much. And it's this quiet, energy-based gatekeeping, this simple mismatch between what visible photons can offer and what the glass's electrons are willing to accept, that begins to explain why something so ordinary as a window pane became, for us, a doorway for light and a wall for almost everything else, a distinction we'll keep gently turning over as we drift further into how this gap itself came to be, the particular size it is. Let's slow down now and follow just one beam of light, a single, narrow thread of it, as it travels from the open air of a room toward the surface of a window pane, because there's a quiet drama happening at that boundary that's easy to miss if you only think about glass in terms of what gets through it in the end. Picture the beam approaching the glass at some gentle angle, not straight on, but slightly tilted, the way light usually arrives when it's coming from a lamp across the room rather than from directly outside. As it nears that invisible seam where air ends and glass begins, something has to happen. Light can't simply ignore the fact that it's entering a different kind of material, a denser thicket of atoms, a different electrical and magnetic environment for it to move through. And what happens, it turns out, is that the beam splits its fate. Most of it presses onward, passing through into the glass and continuing on its way, eventually emerging out the other side into the room or the street beyond. But a small portion of it doesn't go through at all. A small portion bounces back, reflecting off that surface and heading back the way it came, or somewhere near it. This is why, if you've ever sat in a lit room after dark with a window nearby, you can see a faint, ghostly version of yourself in the glass, along with the lamp behind you and the outline of the furniture, even though you know perfectly well the glass is transparent, even though you can also see straight through it to the darkness outside, to the shapes of trees, or a parked car, or the neighbor's porch light. Both things are true simultaneously. The glass is letting light through, and the glass is also reflecting a little of it back. Transparency was never a promise of zero reflection. It never could be, and once you sit with why, the coexistence stops feeling strange and starts to feel almost inevitable. The reason traces back to what glass is doing to light on the inside, at the level of atoms and their electric fields, a process we've touched on already, but that deserves a slower, more careful walkthrough now, because this is where the idea of a refractive index actually earns its meaning rather than being just a number in a textbook. When light enters glass, it isn't moving through empty space anymore. It's moving through a material dense with atoms, and those atoms have electrons attached to them, electrons that respond to the oscillating electric field of the passing light wave. Remember, light is an electromagnetic wave, a rippling handshake between an electric field and a magnetic field, each one regenerating the other as it travels. When that electric field sweeps past an atom in the glass, it gives the electrons there a little nudge, and being bound loosely to their atoms, the way a mass sits on a spring, those electrons oscillate in response. And an oscillating electron is not a passive thing. An oscillating electron radiates its own tiny electromagnetic wave, its own small ripple, matching the frequency of whatever set it moving in the first place. Now here is the part that takes a moment to settle into, so there's no need to rush it. That new tiny wave, radiated by the electron, combines with the original light wave, and with the waves radiated by all the other electrons nearby, all of them nudged in near unison by the same passing field. The combined result is still a wave moving in the same direction as the original beam, still oscillating at the same frequency, since frequency is something the light carries with it and doesn't lose track of along the way. But it's been delayed, ever so slightly delayed. Each little detour through absorption and radiation, each handoff from the field to the electron and back out again, takes a small sliver of time, and multiplied across the enormous number of atoms the light interacts with as it crosses even a few millimeters of glass, this delay becomes measurable. The wave effectively slows down. This is the origin of the refractive index, that number, close to 1.5 for ordinary glass, that shows up so often in descriptions of lenses and prisms and windows. It's simply a ratio, a comparison between how fast light travels in a vacuum, its true unencumbered top speed, and how fast that same light appears to travel once it's threading its way through all those atomic nudges and delays inside a material like glass. A refractive index of 1.5 means light behaves, in an effective sense, as though it's moving at about 2/3 its vacuum speed while inside the glass, not because any individual photon is dawdling, but because the whole process of repeated absorption and re-radiation adds a cumulative lag to the wave as a collective phenomenon. And this slowing down is precisely what causes the bending, the refraction, that gives the phenomenon its name. Think of a beam of light approaching the glass at an angle rather than straight on. One edge of that beam, so to speak, reaches the glass surface a fraction of a moment before the other edge does, simply because of the angle involved. The edge that arrives first begins slowing down first, while the edge that hasn't yet crossed the boundary is still moving at full, unhindered speed through the air. This mismatch, one part of the wavefront slowing while another part hasn't yet, causes the whole wavefront to pivot, to change direction slightly, the way a marching line of people would bend if the ones on one side
suddenly had to wade through shallow water, while the ones on the other side were still striding across dry pavement. The line doesn't break. It bends, smoothly, as a whole. Light does something remarkably similar. This bending is what a 17th century Dutch mathematician named Willebrord Snellius worked out with careful geometric precision, describing exactly how the angle of the bend relates to the angle of approach and to the refractive indices of the two materials involved, air and glass in our case. You don't need his equation itself to hold on to the idea. In plain words, what Snellius found was this: the more sharply the beam's speed changes when it crosses the boundary, the more sharply its path bends, and the angle it enters at plays a role too, with beams striking the surface nearly straight on bending only a little, and beams arriving at a shallow grazing angle, bending far more noticeably. This bending is why a straw in a glass of water looks broken at the surface, why a swimming pool always looks shallower from above than it truly is, and why the glass in your window, thin as it is, still gently redirects the path of the light passing through it, even if that redirection is far too small and far too quickly reversed, as the light exits the far side of the pane and speeds back up again, for your eye to ever notice it happening in ordinary daily life.
But we still haven't quite answered the question we started with, the one about the faint reflection in the window at night. Because if all of this atomic nudging and re-radiating simply slows the wave down and bends its path, why does any of it bounce backward at all? The answer has to do with what happens precisely at the boundary itself, at that thin, almost mathematical seam between two materials with two different refractive indices. Wherever the effective speed of light abruptly changes, wherever the density of those responding electrons abruptly shifts, a small fraction of the wave's energy gets redirected backward, reflected, simply as a consequence of that mismatch, that discontinuity in how the material handles the wave. It isn't that the glass is choosing to reflect certain rays out of stubbornness, it's closer to an unavoidable bookkeeping requirement, a way the wave has to satisfy the physical conditions on both sides of that boundary simultaneously, and reflecting a small portion of the light back is simply part of how that requirement gets fulfilled. The greater the mismatch between the two refractive indices, the greater the fraction that gets reflected, which is part of why the plane boundary between air and ordinary glass reflects only a modest few percent of the light striking it, while a mirror, backed with metal, reflects nearly all of it. So the faint ghost in the window pane at night isn't a flaw in the glass, and it isn't a sign that the glass is somehow failing at being transparent. It's the quiet, necessary signature of the very same process that lets the rest of the light through cleanly in the first place. The same slowing, the same bending, the same boundary-crossing arithmetic playing out in two directions at once. And it's worth carrying this image gently forward as we continue, because there's still more to say about what happens once the beam has made its way inside the glass entirely, and how its path unfolds again on the way back out. Let's stay with that image of light crossing a boundary, and let's ask what happens when a piece of glass has thousands of boundaries instead of two. This is where frosted glass comes in, and it's a wonderfully simple thing once you see it, though it puzzles most people the first time they think about it carefully. Take an ordinary drinking glass, clear and smooth, and set it beside a frosted one, the kind used for bathroom windows or certain lampshades. Chemically, the two objects are nearly identical, same silica, same network of atoms, same fundamental transparency at the level of individual atoms and electrons responding to light. And yet one lets you see clearly through to the other side, and the other gives you only a soft, indistinct glow, shapes without edges, colors without detail. The difference isn't in the material, the difference is entirely in the surface. Frosted glass is made frosted by roughening its surface, either by sandblasting it with fine grit, or etching it with acid, or grinding it with an abrasive. Under a microscope, what was once a smooth plane becomes a landscape of tiny facets, each one tilted at a slightly different angle from its neighbors, like a mountain range shrunk down to the scale of a fingernail. Now think back to that boundary we were just discussing, the seam between air and glass where a small fraction of light bends and a small fraction reflects. On a smooth pane, every point along that seam is tilted the same way, so all the bent light rays, and all the reflected ones, travel onward in the same organized direction. Your eye receives a coherent, orderly pattern of rays, and that coherence is what lets you perceive a sharp image. But on a frosted surface, each tiny facet is tilted differently, so each one bends and reflects its light off in a slightly different direction. The light isn't absorbed, it isn't destroyed. It's simply scrambled, sent off in thousands of divergent directions instead of one unified direction. By the time it reaches your eye, whatever orderly image existed on the other side has been broken into a kind of visual static, still bright, still full of light, but stripped of the detail that depends on rays staying parallel and organized. This is the important distinction to hold onto gently as we go forward. There's a difference between light being blocked and light being scattered. Blocking light means absorbing it, turning it into heat, taking it out of circulation entirely, the way a black cloth does. Scattering light means redirecting it in many directions without destroying it at all. Frosted glass doesn't stop light, it just refuses to let it travel in a straight, cooperative line. And this single idea, scattering without absorption, turns out to be the key that unlocks an entire category of everyday materials that seem opaque, despite being built, at the smallest scale, from perfectly transparent ingredients. Milk is perhaps the loveliest example, because milk is mostly water, and water is about as transparent a liquid as exists in nature. If milk were only water, and dissolved sugars and proteins in true solution, you'd be able to see clear through a glass of it, the way you can see through apple juice, or through vodka, or through a glass of water itself. If milk isn't a true solution, it's an emulsion, cloudy in the literal, scientific sense, dense with countless microscopic droplets of fat and clusters of protein called casein micelles, suspended and drifting through the watery base. Each of these tiny droplets has a slightly different refractive index than the surrounding water, and each one, however small, creates its own miniature boundary, its own tiny site where light bends and partially reflects, exactly the way it does at the edge of a window pane, just on a scale thousands of times smaller. A beam of light entering a glass of milk doesn't travel in a straight line to the far side. It ricochets from droplet to droplet to droplet, bouncing in a different direction every time it crosses one of these tiny internal boundaries, scattering and scattering again, until by the time any of that light exits the glass, it's arriving from every direction at once, rather than following the tidy straight path it would follow through clear water. Your eye can't resolve any structure hidden inside the milk, can't see through to the bottom of the glass, because the information carried by the original beam has been thoroughly scrambled before it ever reaches you. And this is also, worth pausing on for a moment, why milk looks white rather than some other color. All wavelengths of visible light get scattered by these fat droplets in roughly equal measure, so the scattered light reaching your eye is a jumbled mix of every color at once, and a jumbled mix of every visible color, arriving all together, is what your eye and brain interpret as white. Snow, works by almost exactly the same principle, which surprises people, because ice, the solid form of water, is itself perfectly transparent. You can see this clearly enough by looking at a single ice cube, or better yet, an icicle hanging from a roof's edge, catching the afternoon light with a clean, glassy clarity. But pack that same ice into countless tiny crystals, each one jagged, each one oriented randomly relative to its neighbors, with pockets of air trapped between them, and you get snow, which is bright, dazzling white, rather than transparent at all. Every one of those countless tiny crystal faces acts as its own miniature boundary between ice and air, each one bending and partially reflecting the light that strikes it, sending it off toward another crystal face at a slightly different angle, which does the same thing again and again, hundreds or thousands of times, within even a single handful of snow. Layer upon layer of scattering, each layer scrambling the light a little further, until whatever coherent beam entered the snowbank emerges again from somewhere near the surface, having been redirected so many times that it carries no trace of the straight path it might otherwise have taken. None of that light is being absorbed in any significant way. It's simply being turned back, scattered again and again by an enormous number of tiny transparent boundaries, until snow, built from something as clear as ice, becomes one of the most reflective, most resolutely white substances found anywhere in nature. Clouds, up in the sky rather than underfoot, are doing this same trick with water in yet another form, tiny droplets this time, instead of crystals, floating suspended in air rather than packed together on the ground. A single water droplet, if you could isolate it and look through it alone, would be every bit as transparent as the glass in a window. But a cloud contains an almost unimaginable number of these droplets, each one scattering incoming sunlight in its own particular direction, and the cumulative effect of light bouncing from droplet to droplet, again and again, is that same brilliant, structureless white you see looking upward on a summer afternoon. It's the identical physics as the glass of milk, just staged in the open sky instead of a kitchen glass, with sunlight standing in for the beam of a flashlight, and droplets of water vapor standing in for droplets of butterfat. Paper belongs to this same family too, and it's worth sitting with for a moment, because paper is made from wood pulp, and wood pulp is made from cellulose fibers, and cellulose itself, in a pure, dense, unbroken form, is actually transparent. This is not a trick of the imagination. Cellophane, that clear wrapping material generations of households have used to cover leftover food or wrap gifts, is made from regenerated cellulose, chemically not so distant from paper at all, and it's every bit as clear as window glass. What makes ordinary paper opaque rather than clear is the tangled, airy structure the fibers are pressed into during manufacturing, an intricate mat of countless individual cellulose strands crossing over each other at every conceivable angle, with tiny air pockets trapped between them at every turn. Each fiber-to-air boundary scatters light in yet another new direction, exactly as the ice crystals in snow do, exactly as the fat droplets in milk do, and the light entering one side of a sheet of paper is thoroughly scrambled and turned back before it ever has the chance to travel cleanly through to the other side. There's a lovely, almost hidden thread running through every one of these examples, one you can begin to feel gathering itself as we drift toward wrapping up this particular corner of the story. In every case, the transparency was never really lost. It was only ever hidden, buried inside a structure,
so finely divided, so densely layered with internal boundaries, that the light never gets the chance to travel far enough in one direction to reveal it. And that raises a rather different, quieter question, one about what happens on the other end of the scale entirely, when a material has almost no internal boundaries at all, when it's about as smooth and uniform and continuous as matter can be arranged to be.
So let's rest there for a moment, on that quieter question, and let it carry us somewhere new. Because if uniformity is what lets light travel far without being scattered aside, then we should be able to line up a whole series of very uniform, very solid materials, and ask why some of them let light through and some of them stop it cold within a fraction of a millimeter. And this is where it becomes clear, gently and unmistakably, that being solid, being dense, being smooth and unbroken is not the same thing as being transparent. Something else is going on, something deeper than structure alone. Take a piece of metal, a spoon, say, or a coin, warmed slightly in your palm. Metal is about as uniform as ordinary matter gets. Its atoms are arranged in tidy, repeating rows, packed close together, with none of the tangled fiber chaos of paper, none of the jumbled ice crystals of snow. If uniformity alone were the secret to transparency, a polished piece of silver or copper ought to be perfectly clear, and yet you could grind that spoon down to a sheet only a few thousand atoms thick, thinner than a soap bubble's wall, and it would still refuse to let daylight through. Even gold, hammered by old-world gold beaters into leaf so fine it trembles at the slightest breath, so fine that light can just barely worm its way through, transmits only a strange, greenish glow at the very edge of visibility, and even that requires an almost absurd thinness. Why should metal be so stubborn about this, when its structure is orderly in exactly the way that seemed to matter before? The answer lives with the electrons. Inside a chunk of metal, the outermost electrons don't belong to any single atom the way they do in glass. They wander freely across the whole piece, a loose, mobile sea of charge drifting through the fixed lattice of metal ions, like water moving through a bed of gravel. This is, in fact, precisely what makes metal metallic. It's why metal conducts electricity so readily, and why it conducts heat so readily too. And it's also, as it happens, exactly why metal shines the way it does and blocks light the way it does. When a wave of light washes up against that sea of free electrons, the electrons respond almost instantly. They're not tied down, waiting to be nudged into a narrow, particular kind of vibration the way the electrons in glass are. They simply surge in response to the oncoming wave, and in surging, they immediately radiate the energy right back outward, as a reflected wave, before the original light has any chance to slip past them into the depths of the material. That's the shine of polished silver, the gleam of a chrome bumper, the mirror brightness of an old daguerreotype plate. It isn't really a different phenomenon from opacity. It's the same story of absorption and re-emission we followed earlier with glass, only playing out so quickly, so completely, at such a shallow depth beneath the surface, that almost nothing of the original wave survives to continue onward. A sheet of ordinary window glass lets light travel through millimeters, sometimes centimeters, of material before it would be fully absorbed. A sheet of metal stops it within a few dozen nanometers. That's the real difference, and it has nothing to do with tidiness of structure and everything to do with how those electrons are held. Wood tells a related but distinct story, because wood
is neither a sea of free electrons nor a clean lattice of fixed bonds. It's a composite, built from cellulose fibers, not unlike the ones in paper, but bound together with a stiffening substance called lignin, and shot through with countless microscopic channels, the old vessels that once carried water and nutrients up from a tree's roots to its leaves. Even setting aside the fact that wood, like paper, scatters light constantly across all those countless internal fiber boundaries, wood also absorbs light chemically in a way that pure cellulose does not. The various pigments and compounds threaded through real, living wood grain, the same ones responsible for the rich browns and reds and ambers you see in a sanded plank, sit ready with electron arrangements tuned to swallow visible light and convert it into heat. So wood loses on two fronts at once. Its structure scatters, exactly like paper and snow, and its chemistry absorbs, more like a pigment or a dye. Even if you could somehow press wood's fibers into the same dense, boundary-free, cellophane-like arrangement that turns paper transparent, it would still come out tinted and dim, because the coloring compounds themselves have their own separate appetite for visible light. Stone falls into a similar camp, though its story runs deeper still, and rockier, quite literally. Most common stone, granite, sandstone, ordinary concrete, is a jumble of different mineral crystals fused together, each with its own slightly different way of bending light, each boundary between one mineral grain and the next, acting as one more tiny surface for light to scatter from, in exactly the manner we described watching morning fog scatter a headlight beam.
But stone also tends to be riddled with iron compounds and other absorbing minerals, deeply colored ones, which drink up visible light hungrily wherever they occur. This is actually why certain rare stones behave so differently. A thin slice of marble, cut fine enough, will glow faintly amber when held up to a bright light, because marble is mostly a single mineral, calcite, with far fewer internal grain boundaries than ordinary granite, and comparatively little in the way of light-absorbing impurities. Certain gemstones go even further. A clear quartz crystal, grown slowly underground over untold centuries into one single, unbroken lattice with hardly an internal boundary anywhere inside it, can be as transparent as the finest glass, and for essentially the same underlying reason. It comes down, once again, to structure and to absorption together, not to whether a thing counts, in the everyday sense, as a rock. Water offers a cleaner comparison still, because water in its liquid form has almost none of these complications standing in the way. Its molecules are small, they're arranged with a kind of loose, shifting uniformity, and crucially, water molecules have no easily accessible electron transitions that happen to correspond to the energies of visible light. The electrons are all tied up in tight, low bonds that visible light's photons simply don't carry enough energy to disturb, so visible light passes through water with remarkably little absorption, which is why a swimming pool looks clear from above, and why divers can see for many meters through open ocean water on a calm, sunlit day. But water isn't perfectly transparent to every color equally, and this is worth lingering on for a moment, because it's a small detail that quietly explains something almost everyone has noticed, without ever being told why. Water absorbs red light more readily than blue light, even though the difference is subtle, small enough to be invisible in a drinking glass. Over the scale of many meters, though, that tiny difference in absorption compounds and compounds again, until it becomes unmistakable, which is exactly why the deep ocean and even a fairly deep swimming pool
take on that characteristic blue cast, and why the red end of the color spectrum is the first to vanish from a photograph taken many meters below the surface, leaving divers and their equipment bathed in cooler, bluer light the deeper they descend. Plastic sits somewhere in between all of these, which makes sense once you remember that most plastics are, at heart, cousins of glass in one particular respect. Their atoms are typically bonded together in long, tangled molecular chains, not unlike the tangled fibers in paper, but chemically welded together at a much smaller scale, without the same open air gaps between them. When those chains are arranged in a loose, disordered tangle, plastics tend to scatter light and come out cloudy or milky, the way a plastic milk jug does. But when a plastic is manufactured so that its molecular chains lie in a more regular, less disrupted arrangement, or when it's simply cast as a solid, dense, bubble-free block, the way acrylic sheeting is, it can come out remarkably clear enough that thick acrylic panels have replaced glass in aquarium walls, holding back many tons of water, and clear enough that clean, gap-free acrylic can outperform ordinary glass in raw transparency, letting through, in ideal conditions, a slightly higher percentage of the light that strikes it.
And then there is diamond, which deserves its own quiet moment of attention, because diamond takes the whole story to something like its logical extreme. Diamond is pure carbon, every single atom locked into the same tetrahedral bonding pattern as its neighbors, stretching outward through the crystal in a lattice so regular, so thoroughly free of internal boundaries, that a diamond is essentially one single, unbroken molecule, sometimes weighing many carats, without so much as a seam or a grain boundary running through it anywhere. Its electrons are held in bonds so tight, so demanding of energy to disturb, that visible light passes through almost entirely undisturbed, which is precisely why a well-cut diamond can seem to hold and multiply light rather than simply blocking it, why it seems, in a jeweler's hands, to be almost more light than stone. Which brings us, gently, to something a little closer to home than quartz or diamond or ocean water, because your own body, it turns out, has more in common with these transparent materials than most people ever pause to consider. Let's leave the body's quiet transparencies for later, and turn instead to something you can picture more easily in the dark, something ancient and human-scaled, a person crouched by a fire thousands of years ago, watching sand do something sand should not be able to do. Ordinary sand, the kind under bare feet on a beach, is mostly silicon dioxide, the same silica that makes up quartz. On its own, silica melts at a punishing temperature, something like 1600 degrees Celsius, hotter than any campfire, hotter than most ordinary furnaces, hot enough that early humans could not have reached it by accident. Glassmaking, in other words, did not begin the moment someone left sand too close to flames. It began only after people learned to cheat the melting point, to trick silica into softening at a temperature a kiln could actually reach. And the trick, as far as anyone can tell, from broken fragments in the eastern Mediterranean, dating back roughly 3,500 years, involved adding something like ash from burned plants, or natron, a naturally occurring mixture of sodium compounds scraped from dry lake beds in Egypt. These additives are what chemists now call fluxes, and their job is almost administrative in nature. They interrupt the silica's tidy network before it fully forms, lowering the temperature at which the whole mixture goes soft and workable, the way salt scattered on an icy sidewalk lowers the temperature at which water freezes, nudging a threshold that would otherwise sit stubbornly out of reach. But soda alone creates a problem, and it's worth sitting with this problem for a moment because it explains why old glass recipes are more complicated than sand plus ash plus fire. Glass made only from silica and soda dissolves, slowly, unglamorously, in water. Leave it out in rain long enough and it will cloud, pit, eventually crumble, which is not what anyone wants from a window or a drinking vessel, so glassmakers, probably through centuries of trial, rather than any theoretical understanding, learned to add a third ingredient, lime, derived from limestone or seashells, calcium carbonate essentially. Lime stabilizes the glass, locks the structure into something water-resistant and durable, and this three-part formula, silica for the network, soda for the flux, lime for stability, became what's still called soda-lime glass, the ordinary glass in windows and bottles and drinking glasses today, largely unchanged in its basic chemistry for well over 1,000 years, even as the furnaces and tools around it transformed completely. Picture, now, what actually happens inside a furnace when this mixture is heated properly. The silica, soda ash, and limestone are mixed as a dry, gritty powder, almost like a strange flour, and loaded into a crucible or a continuous melting tank, depending on the era and the scale. As the temperature climbs past 1300 degrees Celsius, the powder doesn't simply liquefy the way ice turns to water. It thickens first, becomes syrupy, glowing an orange so bright it's almost uncomfortable to imagine looking at directly, and slowly, the separate grains lose their individual identity, merging into one continuous flowing mass. This is the moment, chemically speaking, when those long chains of silicon and oxygen atoms, which had been sitting as separate rigid networks within each sand grain, begin sliding past one another, tangling together, forming the single interconnected lattice that will eventually cool into transparent glass. It's not unlike watching a crowd of people slowly break down the invisible walls between separate conversations until the whole room becomes one continuous, murmuring mass. Shaping the molten glass has to happen while it's still hot enough to flow, but cool enough to hold a form, a narrow working window that glassblowers learn to feel almost instinctively, judging viscosity by the way the glass drags on the end of a blowpipe. The ancient technique of glassblowing, invented sometime around the 1st century BCE, probably in the region that is now Lebanon or Syria, changed everything about how fast and how cheaply glass could be made, because a single breath of air, pushed through a hollow rod into a blob of molten glass, could inflate it into a hollow vessel far faster than the older, laborious method of grinding a shape from a solid block, or slowly winding threads of glass around a sand core. And it's worth pausing on the physics of that breath for a moment, because it's a small, elegant demonstration of pressure and surface tension working together. The molten glass, still soft and taffy-like, resists stretching just enough to hold its shape once the air stops pushing, the way a soap bubble holds its curved surface through the same quiet balance of internal pressure and surface tension, except that glass, unlike soap film, keeps that shape permanently once it cools. Modern window glass, since the middle of the 20th century, is rarely blown at all. Most of it is made by what's called the float process, developed by Alastair Pilkington in England in the 1950s after years of expensive, frustrating experimentation in which molten glass is poured onto a bath of liquid tin. Glass and tin don't mix, and because liquid tin is remarkably flat and level under gravity, the glass floating on top of it spreads out into a sheet of astonishing evenness, flat on both sides, without any of the ripples and thickness variations that plagued older, more mechanically rolled sheet glass. This is part of why old windows, The ones in genuinely historic buildings sometimes show a faint waviness when you look through them at the right angle, a gentle distortion in the reflections, while modern windows look almost eerily perfect, optically neutral, letting light through without adding any visual commentary of their own. Once glass is shaped, it cannot simply be left to cool in open air, and this is a detail that surprises people who assume glassmaking ends the moment the object takes its final form. Cooling glass too quickly creates enormous internal stress, because the outer surface hardens and contracts, while the interior is still hot and soft, and that mismatch leaves the finished piece full of trapped tension, the kind of tension that can cause a glass to shatter spontaneously, sometimes days or weeks later, for no visible reason at all. The solution is a slow, controlled reheating and cooling process called annealing, in which the glass is brought back up to a temperature just below its softening point, and then cooled gradually, over hours, sometimes over a full day for large or thick pieces, allowing the internal structure to settle evenly, rather than freezing in place under strain. Annealing ovens, called Leers in the glass industry, are essentially long, slow-moving tunnels of gradually decreasing heat, and a piece of glass that skips this step, even one that looks perfectly finished, carries an invisible fragility that properly annealed glass does not. Composition, though, is where glass really begins to branch into different personalities, each suited to a different kind of demand. Ordinary soda-lime glass expands and contracts noticeably with temperature changes, which is fine for a window, mildly annoying for a drinking glass filled with something hot, and genuinely dangerous for cookware, because a sudden temperature swing, pulling a dish from a hot oven onto a cold countertop, can create enough internal stress to crack it outright. Borosilicate glass solves this by swapping some of the soda and lime for boron oxide, which changes the underlying atomic network just enough to make the material expand and contract far less with heat, something like a third as much as ordinary glass. This is why laboratory beakers and, later, kitchen bakeware, developed under brand names like Pyrex in the early 20th century, are made from borosilicate formulas, a change first driven by railroad engineers needing lantern glass that wouldn't shatter in cold weather, later adapted by a Corning scientist's wife, who, according to the often repeated account, baked a cake in a cut-down battery jar made of the new heat-resistant glass, and found it browned more evenly than her usual dish. Optical fiber pushes composition and precision even further, because the entire purpose of a glass fiber is to carry light for kilometers with almost no loss, which means the silica has to be purified to a standard almost unimaginable in ordinary glassmaking, with impurities measured in parts per billion rather than parts per thousand, since even a faint trace of iron, the same iron that gives old window glass its faint greenish tint when viewed edge-on, would absorb and scatter enough light to make long-distance fiber communication impossible. Color, meanwhile, comes almost entirely from small, deliberate impurities, metal oxides, stirred into the melt in tiny quantities that would ruin fiber optics, but that, in a stained glass window, become the entire point. Now let's turn from the glass itself to the things we do to its surface, because so much of what makes modern glass feel almost invisible, or almost mirror-like, or almost impossibly strong, has nothing to do with the raw material and everything to do with a thin layer added afterward, sometimes only a few hundred nanometers thick, thinner than the wavelength of the light it's meant to control. Start with a puzzle that anyone who has worn glasses will recognize without necessarily naming it. A bare piece of glass reflects a little bit of every ray that hits it, something like 4% at each surface, for ordinary glass viewed straight on, which sounds trivial until you remember that a lens has two surfaces, and a camera might have a dozen lens elements, and a window might be one pane of several. Reflections stack. Look at an uncoated eyeglass lens under the right light, and you'll see a faint, ghostly double image of a bright window or lamp, light that bounced off the back surface, then the front surface, then finally escaped toward your eye, arriving a fraction of an instant late and slightly displaced. This is why early photographic lenses, before the 1930s, tended to produce images with a soft veil of scattered light in high-contrast scenes, a kind of low-grade fog that photographers simply accepted as an unavoidable cost of using glass. The fix, once discovered, turned out to be almost embarrassingly elegant, and it rests on the same wave behavior that explains why a soap bubble shows swirling colors. If you coat a lens with a layer of material whose thickness is tuned to exactly 1/4 of the wavelength of light you're trying to suppress, something remarkable happens. Light reflecting off the top of that thin coating and light reflecting off the boundary between the coating and the glass underneath travel very slightly different distances, and because of that quarter wavelength offset, the two reflected waves come back out of step with each other, peak meeting trough, and they cancel. Not perfectly, and not for every color at once, since a single coating thickness can only be tuned for one wavelength, which is why coated lenses often show a faint purple or greenish sheen. That's the light the coating couldn't fully cancel, usually chosen to fall in a part of the spectrum the eye is less sensitive to. Modern lenses stack several coating layers of different thicknesses and different materials, each tuned to suppress a different band of wavelengths, so that the combined effect flattens reflection across nearly the whole visible spectrum. The physicist Catherine Blodgett, working at General Electric in the 1930s, is often credited with the first practical anti-reflection coating, built one molecule-thick layer at a time using a technique she'd developed for laying down films on water, and by the end of the decade, lens coating had become standard practice in serious optics, which is part of why a modern camera lens looks faintly tinted blue or amber when you catch it at an angle, and part of why old uncoated binoculars from a flea market often look strangely hazy by comparison. Reflection can also be tamed by controlling not just how much light bounces, but which direction it vibrates in, and this is where polarization enters the story, quietly, in ways most people never think to ask about. Light, as a wave, oscillates in a direction perpendicular to the direction it's traveling, and ordinary light from the sun or a lamp is a jumble of waves oscillating in every possible direction at once. But light that reflects off a flat, non-metallic surface, water, a car hood, a wet road, tends to become partially polarized, meaning the reflected glare vibrates mostly in one direction, roughly parallel to the surface it bounced from. A polarizing filter is essentially a microscopic grid, invisible to the eye, but real at the molecular level, that only lets through light vibrating in one particular orientation. Rotate a pair of polarized sunglasses 90 degrees, and, if you're looking at glare off a lake, you can watch the reflection nearly vanish, and then return, because the lenses are simply blocking the direction the glare happens to favor. Edwin Land, who later founded Polaroid, worked this out as a young man in the 1920s, grinding and aligning microscopic crystals into sheets, motivated partly by the very practical goal of reducing headlight glare on nighttime roads, an application that never quite caught on the way he hoped, though the sunglasses and camera filters that came from the same research became enormously common. Strength is its own engineering problem,
separate from reflection, but just as central to how glass fits into daily life. And here the story splits into two rather different strategies.
Tempered glass,
The kind used in car side windows and shower doors, is made by heating a sheet of glass until it's nearly soft, and then chilling its surfaces rapidly with jets of cold air, while the interior stays hot a little longer. As the interior finally cools and tries to contract, it's already hemmed in by a surface that solidified first, and the result is a permanent tug-of-war frozen into the glass, with the outer layers held in compression and the inner layers held in tension, a bit like a stretched rubber band wrapped inside a rigid shell. That stored compression makes tempered glass considerably harder to crack than ordinary glass. But it also means that once a crack does manage to start, usually at some small chip or flaw where the balance of stresses gets disrupted, the whole sheet releases its stored energy almost instantly, crumbling into thousands of small, relatively dull-edged pebbles rather than long, dangerous shards. This is precisely the outcome car designers wanted after decades of injuries from ordinary plate glass windshields, shattering into blade-like fragments in collisions. Laminated glass solves the same safety problem from a different angle entirely, one that predates tempering by about 3 decades. The French chemist Édouard Benedictus is often credited with the discovery, and the story, whether or not every detail survives scrutiny, is charming enough to have stuck. In 1903, he supposedly knocked a glass flask off a shelf in his laboratory, a flask that had once held a cellulose nitrate solution which had evaporated, leaving a thin plastic film coating the inside, and the flask cracked but held its shape instead of shattering. Laminated glass takes that accident and formalizes it, sandwiching a thin, tough plastic interlayer, typically polyvinyl butyryl, between 2 sheets of ordinary glass. When laminated glass breaks, and it still breaks in the sense that cracks spread across the surface, the plastic layer holds the fragments bonded in place, rather than letting them scatter, which is why a cracked windshield tends to remain as one crazed but intact sheet, rather than falling away entirely. Windshields use laminated rather than tempered glass, specifically because the driver needs to keep some visibility, even through a damaged pane, whereas side and rear windows, where visibility during a crash matters less than getting out quickly, use tempered glass instead. Windows themselves have quietly absorbed a great deal of engineering, aimed at a much less dramatic goal, keeping heat where you want it. A single pane of ordinary glass is a poor insulator, letting heat pass through fairly easily by conduction, which is part of why old houses with single-pane windows feel drafty near the glass even when there's no literal draft, since the cold pane simply pulls warmth out of the nearby air and radiates coldness back at you. Double and triple glazing helps by trapping a layer of still air, or sometimes an inert gas like argon, between panes, since gas is a much worse conductor of heat than solid glass. But an even subtler trick involves coating one interior surface with a layer of metal or metal oxide only a few atoms thick, called a low emissivity or low E coating, so thin it doesn't noticeably dim the view or add any visible tint. Yet it reflects a meaningful portion of infrared radiation, the invisible heat radiation that would otherwise pass freely through plain glass. In winter, this bounces indoor heat back into the room instead of letting it radiate out through the window at night. In summer, oriented correctly, it can bounce a good portion of the sun's infrared heat back outside before it ever warms the room, all while visible light passes through largely unaffected, which is how a modern window can look completely ordinary and yet perform in a way 19th century glass simply couldn't.
There's a small observation many people have made without ever quite asking why it happens. Stand outside a lit house after dark and look at its windows, and they seem almost black, like small mirrors, even though during the day the same panes of glass looked perfectly transparent, showing curtains or furniture or the shape of a room beyond. Nothing about the glass has changed. What's changed is the balance of light on either side of it. During the day, the amount of light coming from outside is enormous compared to what's inside, so nearly all the light reaching your eye through the window is light that traveled through the glass from the brighter side, and the small amount of light reflecting off the glass's surface gets lost against that flood, the way a candle is invisible in daylight but obvious in a dark room. At night, that ratio flips. The room behind the glass may be dim to begin with, and whatever light it does produce has to compete with almost nothing coming from outside, so the faint reflection off the glass surface, normally too weak to notice, becomes the dominant thing your eye picks up. You're not seeing into the room anymore so much as seeing a dim mirror image of whatever's near you outside, layered thinly over a room you can barely make out behind it. It's the same physical process at every hour. A small fraction of light always reflects off a glass surface and a larger fraction always passes through. But which of those two effects wins depends entirely on which side is brighter, which is also why, from inside a lit room at night, the window can feel like a mirror in the opposite direction, showing your own reflection back at you instead of the dark yard beyond. A related puzzle turns up if you've ever looked at the edge of a pane of glass, the thin strip visible where it sits in a frame, or stacked several sheets of glass together, like looking through a bookshelf of glass panels from the side. Rather than looking clear, that edge often shows a distinct greenish tint. This seems strange at first, since the same glass viewed straight through, face on, looks colorless. The explanation comes back to something mentioned earlier in this account, the tiny amount of iron that gets into glass from the sand used to make it. Ordinary sand almost always contains a trace of iron oxide, and even in very small concentrations, iron absorbs a bit of red light and lets more green and blue light through, giving the glass a faint green cast. Looking through a single pane face on, the light only travels perhaps a few millimeters through the glass, far too short a distance for that faint absorption to add up to anything visible, so the pane looks clear. But looking along the edge, the light travels through inches of glass instead of millimeters, so that same weak, per millimeter tint gets multiplied many times over, the way a lightly tinted drink looks nearly colorless in a shallow glass but distinctly colored in a tall one, even though it's the same liquid at the same concentration. High-quality optical glass and some premium architectural glass use much purer raw materials, specifically to minimize this iron content, producing what's sometimes called low iron or water-white glass, which stays nearly colorless even edge-on or in thick sections, and which is noticeably more expensive to produce for exactly that reason. Glass making rainbows is a related but separate story, one that has less to do with any impurity and everything to do with the basic physics of how light bends when it changes speed. When white light, which is really a mixture of many different wavelengths corresponding to different colors, enters glass at an angle, it slows down, and that slowing causes it to bend, a phenomenon called refraction. The detail that produces a rainbow is that different wavelengths slow down by very slightly different amounts, so they bend by very slightly different angles, an effect called dispersion. Red light bends least, violet light bends most, and everything in between spreads out proportionally, so a beam of white light that enters a prism or a cut piece of glass as a single beam exits as a fan of separated colors. A flat pane of window glass, with its two surfaces perfectly parallel, actually cancels most of this effect out, since the light bends one way entering and back the other way by nearly the same amount leaving, recombining into white light again on the other side, which is why ordinary windows don't normally throw rainbows onto your wall. Cut crystal,
faceted glass ornaments, and old glass with slightly uneven or beveled edges lack that parallel cancellation, so they let the spread of colors persist long enough to become visible, scattering little rainbow patches across a room when sunlight catches them at the right angle, a small everyday echo of the same principle Isaac Newton used deliberately with a prism in a darkened room in the 1660s to show that white light was secretly a mixture of colors all along.
Ultraviolet light raises a different kind of question, since it's invisible, and yet whether glass blocks it or not has real consequences, from sunburn through a car window to the fading of fabric and photographs left near a bright window for years. Ordinary window glass actually blocks most of the shorter, more damaging ultraviolet wavelengths quite effectively already, simply because of how strongly ordinary silica-based glass absorbs light at those wavelengths without needing any special additive. But it's considerably less effective at blocking a longer wavelength band of ultraviolet, the kind mostly responsible for skin aging and gradual fading rather than sunburn itself, and this is why people can get a mild tan sitting near a closed car window on a long sunny drive despite feeling like they're fully protected by glass, and why upholstery and curtains near a sunny window slowly bleach over months and years even though nobody in the house has ever been sunburned indoors. Specialized coatings, similar in spirit to the low emissivity coatings used for heat control, can be applied to glass specifically to absorb or reflect this remaining ultraviolet band more completely, and this is a normal feature on high-end sunglasses lenses, some car windshields, and museum display cases, protecting sensitive paintings or documents from decades of cumulative light exposure. There's an old claim about window glass that resurfaces every so often, the idea that panes in centuries-old buildings are visibly thicker at the bottom because glass is technically a slow-flowing liquid, oozing downward over hundreds of years under its own weight. It has a certain appeal, since it sounds like a quietly dramatic secret hiding in plain sight in old churches and farmhouses. But it isn't accurate, at least not in any way that could produce the thickness differences actually observed. Glass at room temperature is, for all practical purposes, a solid, and the calculations physicists have done on how a material with glass's measured viscosity would behave suggest that any flow over even many centuries would be far too small to notice, certainly not enough to visibly thicken a window pane's bottom edge within a human lifetime or 10. The real explanation is much less romantic and comes down to how old glass was made in the first place. Before the float glass process existed, panes were often produced by spinning a blob of molten glass into a flat disc, a method called crown glass, which naturally produced a sheet that was thicker toward the center and thinner toward the edges, or by other hand methods that similarly left panes with uneven thickness across their surface. When glaziers installed these panes, it made structural sense to set the thicker edge at the bottom, both because it seated more solidly in the frame and because it simply looked more stable to the eye, so the unevenness people notice today in old windows is the fossilized memory of an old manufacturing process, not evidence of centuries of gradual flow. And there's one more everyday oddity worth sitting with before this account settles into its final threads: the fact that something you can see straight through can still very much be hot to the touch, or capable of shattering from heat it never even fully let inside. Yes, that's true too, and it's worth pausing on for a moment, because it circles back to almost everything this account has already walked through. A glass window left in the sun grows warm not because the light heating it passes through unchanged, but because some small fraction of that light, along with the surrounding air and the infrared radiating off nearby warm surfaces, gets absorbed by the glass itself, jostling its atoms just slightly and that jostling is what we register as heat. A window can feel warm under your palm while still doing its main job of letting the visible world through essentially untouched. And thermal stress, the kind that can crack a pane when one part of it heats unevenly, faster than the rest, happens for reasons that have nothing to do with transparency and everything to do with expansion, with one region of the glass trying to stretch while a shaded region right next to it stays put, until the strain between them becomes more than the material can hold. None of that contradicts anything said earlier about how glass lets light through. It simply reminds us that transparency was never the same thing as absence. The glass is still there, still made of atoms, still capable of taking in energy and doing something with it, even while visible light glides across it as though barely anything solid stood in the way at all. So here, gently, is the whole shape of it, gathered up one more time, the way you might gather a day's scattered thoughts before finally letting your eyes close. It began with a wave arriving, ordinary sunlight or lamplight, an electromagnetic ripple, traveling untouched through empty space until it reached the front surface of a pane of glass. And what met that wave there weren't tiny gaps for it to slip through, no secret tunnels between atoms, but the electrons belonging to the atoms themselves, clouds of charge surrounding oxygen and silicon and the network they form together. Those electrons felt the wave's oscillating electric field and answered it, vibrating in sympathy, the way a struck tuning fork can make a nearby fork hum without anyone touching it a second time. Whether that vibrating electron simply passed its energy back out as a new wave, continuing the journey, or whether it held onto that energy and turned it into heat, depended on something almost embarrassingly specific, a question of arithmetic. Every atom has electrons sitting in certain allowed energy levels and never in between, the way a ladder only offers you rungs, not the space separating them. For an electron to truly absorb a photon and jump upward, the photon's energy has to match a gap between rungs almost exactly. In glass, and in the particular chemistry of silicon dioxide with its added ingredients, it happens that the gap between an electron's resting level and the next level above sits wider than the energy carried by any photon of visible light. Red light, green light, violet light, none of them arrive with quite enough energy to make that jump. So the electrons cannot properly absorb these photons the way they'd absorb, say, ultraviolet light, which does carry enough energy to bridge that same gap, which is exactly why glass quietly blocks the sunburn-causing wavelengths a little further along the spectrum, while letting the visible middle stretch straight through. Instead, for those wavelengths that don't fit the gap, something gentler happens, something closer to borrowing than owning. The electron shifts briefly, absorbs the wave's energy just long enough to send an answering wave back out in the very same direction the original was traveling, and does this again and again as the light crosses trillions of atomic layers within the glass, each handoff so close to instantaneous that from the outside it looks like nothing paused at all. It is this repeated absorbing and releasing, this relay race passed from atom to atom in near-perfect step, that constitutes what we call transmission. Glass letting light through, not by getting out of the way, but by continuously catching and passing the wave onward, like hands moving a bucket down a line. That relay, though, moves a little slower than light travels through the vacuum of space, and that small delay is the entire reason a straw looks bent where it enters a glass of water, the entire reason glass can bend, focus, and magnify. The wave doesn't slow down everywhere identically either. Different colors, having slightly different energies, and therefore interacting just a touch differently with those same electron clouds,
get delayed by very slightly different amounts. So a beam of white light passing through a glass prism spreads gently apart into its component colors. The same physics letting a chandelier scatter small rainbows across a wall on a sunlit afternoon. And where the glass itself isn't perfectly uniform, where there are microscopic bubbles, or seeds as old glassmakers called them, or subtle variations in composition throughout an otherwise clear pane, some of the light doesn't continue politely forward at all. It scatters, deflected off in new directions by these tiny irregularities, which is part of why old, imperfectly made glass can look faintly cloudy or hazy under close inspection, even while still letting the bulk of light through well enough to see a garden or a street through it. Modern glass, made under far more careful and controlled conditions than glassmakers a few centuries ago could manage, minimizes these irregularities enormously, which is one reason a contemporary window looks so much clearer than one salvaged from an old cottage. None of this transparency was ever guaranteed by glass being glass in some general sense. It came from specific choices in composition. Sand melted down with soda ash and limestone in careful proportions, iron impurities kept as low as practically possible, since iron is what gives thick glass its faint greenish cast when you look through the edge of a pane, rather than straight through its face.
And often, sitting invisibly on top of all that careful chemistry, a further layer engineered on purpose, a coating thinner than a wavelength of light itself, designed to reduce reflection or to reflect infrared heat back outside a building in summer, or to let certain wavelengths through while turning others away. These aren't accidents of nature. They are the accumulated, deliberate craft of people working out, generation after generation, exactly how to make an inanimate arrangement of atoms behave the way our eyes want it to behave. It's worth remembering, gently, before this account lets you go, which parts of it were solid, careful physics, established through decades of careful experiment and confirmed again and again, and which parts were simplified sketches offered only because a sketch is sometimes the kindest way to hold an idea steady in the mind long enough to fall asleep beside it. The image of electrons as tiny bells ringing in sympathy, of light as a bucket passed hand to hand down a silent line, of energy gaps as rungs on a ladder. None of these are the whole truth in the strict mathematical sense a physicist would write out with equations, but each one points honestly towards something that really is happening, without asking you to hold the full weight of quantum electrodynamics in your mind at this hour. That's the quiet difference between a metaphor and a lie. A good metaphor bends the truth's shape gently enough to fit inside a tired mind, without breaking the truth itself. So let it end where it started, with something almost too ordinary to notice. A window nearby, in whatever room surrounds you now, dark or half-lit, holding back the night air, or simply resting in a wall between one silence and the next. Light might be crossing it as this line reaches you. Moonlight, streetlight, the last colors of a sky finishing its slow fade, entering as a wave, meeting the electrons of atoms that stopped moving long enough to become solid, and passing through, atom to atom, almost too quickly to have taken any time at all, and yet, if you had asked it to explain itself, it would have needed this whole long unwinding, gap by gap, wave by wave, to be understood even this far. Nothing more needs explaining tonight. The glass will keep doing what it does, quietly, patiently, without needing your attention, whether you're awake to consider it, or already drifting past thought altogether. Rest well.